Welcome to the lesson number 7 on Kubernetes networking and storage. In this lesson, we will be talking about a couple of things. The network in Kubernetes is almost the important thing because through which you will decide whether you want to expose the workload or application to the outside world or not. And then how do you interact internally within multiple different applications in typical microservices scenario. So we need to understand the Kubernetes networking architecture. And then we will talk about Kubernetes volumes, explain about persistent volume, and understand the persistent volume lifecycle. And then we'll see what all different additional persistent volume we can use, which is outside of the Kubernetes and available and allowed in the Kubernetes kind of architecture. Kubernetes networking. Overview of Kubernetes networking. It is a communication model used by Kubernetes to connect its components. Uses a flat network structure. Eliminates the need to map ports between hosts and containers. The need for Kubernetes networking. Kubernetes enables applications to share machines. It helps coordinating ports across several developers, which is extremely challenging. Sharing machines necessities that no two applications use the same ports. Also, users are exposed to cluster level issues beyond their control. System is complicated by dynamic port allocation. Every application must use ports as flags. Services must know how to find one other. API servers must know how to insert dynamic port numbers into configuration blocks. Instead of dealing with this, Kubernetes uses a different method. Kubernetes networking model. Basic requirements imposed by Kubernetes for networking implementation. Without network address translation or NAT, all pods can communicate with each other. Without network address translation, all nodes can communicate with all pods. IP address that a pod sees is the same as the IP address that other sees. Kubernetes networking model is easier in general, more compatible with Kubernetes goal of enabling low friction app porting from VMs to containers. If the job had previously ran in a virtual machine, it had an IP address and could communicate with other virtual machines in the project. Kubernetes networking issues, the issues it generally tries to solve. Highly coupled container to container communication is generally solved by pods and local host networking. Pod to pod networking, communication between pods are by default. Pod to service communication uses service to enable the communication. External communication between internet and services. Let's go a bit deeper into Kubernetes networking architecture. Now, if you think about this cycle of container to container networking, right? If it is a device or a virtual machine, it can communicate directly with an Ethernet device today. So if you have two laptops connected in a network, they use the Ethernet device to communicate each other, right? Each process on a machine can communicate under a network namespace, um, especially for Linux, assuming that you are running them on Linux. And then namespaces builds its own logical networking stack along with the network devices, firewall, rules, routing table, etc. So you get to see that option by default present within the scope. So we don't have to do that. They're already, we just need to pick it up. When a process begins, it automatically assigns to the root network namespace in the Linux context. And the network namespace gives the process an access to the external IP address thing. So you basically have this cycle running in. Now, you need to understand one thing very clearly that within a Kubernetes pod, you are basically running a container. A container is all about running one single process at a time. So container runs one process. The moment container is running, it is actually using one process. And that process, if it needs an IP address, need to talk to something else outside of the container, then it uses that network. Now for the container to container networking, right? If you think about that, if you group one or more container within a pod, each with its own namespace, then all the container in the pod share the same IP address and port space. So you basically will be able to use a local host and connect to each other if they belong to the same pod. So you can actually interact with the container one, with the container B, if they are in the same pod using a local host endpoint. And then pod to pod networking connects the containers with different pods. So, for example, if you want to talk to container one with the container A, which are in two different pods, then it has to use this root network namespace, go via that and come. So there is no direct communication available over here in this space. Now, in a pod to pod networking scenario, it uses a classless interdomain routing or CIDR, right? And that exists with each node. So the moment you spin up a node, you get a CIDR configured for you, which basically contains a list of unique IP addresses assigned to the pod on the node. So the moment you create a pod, it gets an IP address assigned by the node, right? Which ensures also that each pod has its own IP address. So there will be no pod without any IP address. So when if you see list of pods running in your cluster at any given point in time, you will see all of them will have the IP address. Now, how that IP address is exposed, right? How much they can go beyond what is what something we'll discuss little later, but you understand that they all have IP address. That's the primary requirement. Then when you think about moving pod to pod, if you have, let's say, a container running in the pod one, and then they need to talk to pod two, they cannot talk directly. So they go via the root network. So which means that there'll be a node level root network, which is a Linux based mechanism, which uses a virtual Ethernet concept or VEth. So you can have a virtual Ethernet created, which is already there, which essentially talks to the host, in this case, that node network, and then go via that host to the pod network, which is another pod within that same cluster, right? And this is sitting either within physical machine or a virtual machine, right? So the root namespace assigned to one of the pair while the pod namespace is assigned to others. So you think about this as your local network Ethernet card, right? You get an Ethernet card for each pod, and then you have that Ethernet card available at the root level via which you communicate, right? You do not have a direct connectivity. You always have to go via that. Now, Kubernetes pod to service networking basically allow the dynamic replacement as per the need, right? So for example, when you have a deployment creator which can um, create pod as and when required, and then the moment you say that I want to increase the capacity, it basically goes ahead and increases the whole capacity immediately. It's not a very long lasting solution because each pod gets created and deleted quite frequently. If we start capturing those IP addresses, they are not fixed, right? Instead, if we use the service model, which we discussed earlier, then it has a DNS, name resolution. So no matter whether I have a new set of IP addresses, if it is a 3 or 5 number of IP addresses, I will still be able to interact with the pods as I may want to do that, right? It will ensure the communication between the pod, and it will help us extend our network outside of the Kubernetes cluster. Now, the service using the selector, which is again a level concept. So you basically create pod with level, and the service says that I want to observe this level. Okay. And then whatever pod you create using that level will be part of that service. Right. So that's how it keeps track of the pod state. And then it also keeps track of the pod IP addresses. And that's how it creates those endpoints in the container, right? So it basically creates those IP addresses. It allocates a single virtual IP address to the set of pod IP addresses. So it basically does a bit of load balancing as well. So you may have 5 pods running behind a single service, let's say front end. All of them has their own IP addresses, but a service provides you another IP address, which is basically an abstraction on top of these IP addresses, right? So you guys get that bit of load balancing capability built into that. So any traffic which is directed to that virtual IP address is distributed to the pod linked with them. So it is done for us. It's one of the heavy liftings done by Kubernetes for us. Because pod can be created and removed using a service IP address without disrupting the overall communication. It's a very, very loosely coupled architecture, which means that you can create a pod and then you can create a service separately. And then if you delete the pod, the service still keeps waiting if there is no pod with the level it is observing. The moment a pod comes, it just takes that IP address in, updates its IP table, and then makes that routing mechanism automatically. So this is quite helpful in a large distributed scenario where you don't know any state what will happen to that. Now, what happens when you have this kind of thing, right? So, and you expose it via service is that it uses this root network namespace, and then through the IP table, it has that IP address which it exposes to the outside world. It could be to another VM within the same cluster of that Kubernetes environment. It could be to the external world, like outside of the cluster altogether, right? It doesn't really matter. At the end of the day, it needs to actually send you the IP address back to the end user, which they will be using, right? So it can be a local IP address. It could be can be a public IP address, depending on how you want to expose it. Let's go a bit deeper into Kubernetes networking architecture. Now, when we want to expose the service to the external world, which means that you want to give a public IP address so that people can reach to this service via a public IP address or a DNS understood by the public IP address, you require internet connectivity for that, right? And these are thing which is commonly used in the cloud kind of scenario. So when you build a Kubernetes cluster in any public cloud, right, you have the ability to expose your API or endpoint to the external world by using load balancer kind of thing. So you need external load balancer to do that, not the default service. Now you can think of extending your service in two different ways. One could be egress way, right? Uh, Traffic coming from Kubernetes service to the outside world. So, for example, you go reach out to any third party website, fetch some data, and bring that back to your thing, right? So you might want to integrate with a lot of SaaS solution. You can do that. Or Ingress, when you basically host your website in Kubernetes and allow people to interact with that, right? You can also define policy to regulate the traffic in and out using whitelisting or blacklisting. So you can say that I will allow only these range of IP addresses in for my communities because they are my known customer. Rest all I will simply deny, even if it is a public uh, IP address or public endpoint for me. Now, in terms of egress networking, when you go reach out to internet from your pod, right? You take the same route, right? You have a pod, you go to the root network of your virtual machine. In this case, this is a node for Kubernetes, that's a worker node. And then eventually you can reach out to the internet gateway and then go up to the network, right? So the internet gateway basically comes handy here because it maps that IP address between the user and the machine where the node is hosted using a network address translation or NAT. But one thing this internet gateway can't really do is that it can't really map the node's individual port, right? So you basically get to see that each node gets some IP address assigned, right? And then the pods basically creates within that node, and they also get IP address. So this gateway cannot reach out to that level. So you have to actually think from a holistic perspective, and then let this gateway come handy only when you reach at the node level, not at the pod level. So you can't really expose pod directly to the internet without going via this channel. Now, in terms of egress networking, you also have IP table concept, right, which Kubernetes uses, and then cluster IP to complete the communication. So you translate, put everything in the IP table, and then you expose it via the internet gateway. Now, in terms of ingress networking, right, so you basically need to set up an ingress load balancer, right? So it is nothing but a collection of rules that enables the inbound connection. So and then configure to provide the service outside through reachable URL. Imagine that you are hosting a website and that has a HTTP endpoint, right? So the Ingress network serves an entry point to the Kubernetes cluster. So you give an URL to your end user and you say that's how you reach out to my application. I may have hundreds and thousands of pods running behind the scene, but you don't have to care because that's your entry point. It basically will manage my external access. So for in terms of authentication and authorization, I don't have to apply all this complexity in all my container and pods I'm writing. Rather, I'll be focusing in this and say that, hey, you are the set of users who are authenticated now and let me do the authorization. So you put those things in at this layer and then you let your traffic in once they're satisfied with this, right? So you basically end up seeing something which is quite flexible and loosely coupled, but rock solid in nature because it doesn't really bother the developer to build this authentication individually in each of these containers. volumes. Kubernetes networking uses third-party tools. Kubernetes demands a network model that can be implemented with third-party solutions like Flannel, WeaveNet, Calico, etc. Kubernetes storage. Kubernetes storage is based on volume concepts. Ephemeral volumes, commonly referred to as volumes. Persistent volume is intended for long-term storage. Pods are the basic execution unit in the Kubernetes object model. To select the appropriate storage type, understand how it is provisioned to the pod. Pod can be made up of one or more containers. Image mounted at the root of the file system hierarchy in each container. Volumes mounted at specified paths within that image to any or all of the containers. What do you understand by the Kubernetes volume is that they are most basic storage unit, and it links the storage to the pod and gives the container a space to work on, right? And this volume can be used to, let's say, cache the temporary data, share file among the container, load data into the pod. So if you have a preload option through init container, pull some configuration detail in your storage, and then the other container can pick it up from there. So all these things you can think of using Kubernetes volume. Volume manifests itself in three different ways. You can use the pod's file system, which will persist if one of the pod container crashes and restarts, right? And you can share the data between container in a single pod, and it's quite easy to do that. You can accomplish it by applying the same volume to all these desired container within the pod. So you can map the drive to all the container within a single pod, and they will be able to see the same file from every container. So volumes are basically defined in the context of pod, right? And then volume becomes unmanageable and their life cycle is tied to the pod. So then remember, the moment you go ahead and delete a pod gets killed or recreated, that is gone. Okay, so you lose everything. So you tend not to use this quite often when you need to ensure the files you're working on could be half done and maybe need it later point in time when I get a new pod. So you will choose something which is persistent in nature, not ephemeral in nature, right? So that's when this persistent thing comes into play. But ephemeral volume is quite handy in quickly doing some temporary stuff. And there are types of ephemeral volumes we have available, right? Which is tightly coupled with nodes lifetime, right? And then it is removed when a node goes down. So this is one level up of the Kubernetes pod, right? A pod is hosted within a node, right? So when, let's say, you deploy a pod, it goes ahead and finds an available node and deploys the pod in that node. And you can use something like an empty directory or host path to really interact with this Kubernetes node level ephemeral volume. Now, when you need more stable volume beyond the node, because node is at the end of the day is a virtual machine, or can also be killed, right? And can also have a new node coming up. And Kubernetes is not bothered about this node thing because it doesn't really store anything at the node level from a Kubernetes management perspective. So imagine that if a node goes down, which hosted some 50 pods internally, and if there is a new node available which has a space, Kubernetes will immediately recreate those pod in the new node, right? So if you use empty directory or this ephemeral storage, which is in the node perspective, you will basically not be able to find those files. In those cases, you need persistent volume. So persistent volume, imagine that it's a map drive, and that map drive is somewhere outside of the Kubernetes cluster, right? It can be inside of the Kubernetes cluster, but it could be outside of the Kubernetes cluster. In those cases, it's for long-term storage. We use a lot of cloud volume mechanisms, so cloud storage mechanisms, so it's not part of the Kubernetes cluster, but I can map it here. Now it uses something called a concept called a persistent volume claim to really bring in those mechanism into play. So it helps us, let's say, have those thing um, attached to our application. We can now say, hey, go ahead and then use this persistent volume within my container, right? So then it will be doing that. Now, there are several types of volume supported. You can see that these are the types available. And you can see some of the things like AWS Elastic Block Storage, Azure Disk, Azure Files, and then you have all this cloud storage, and even you have iSCSI, NFS, and different type of persistent volume thing, including the persistent volume claim, which you can attach to your um, container and then work happily. Now, to understand the persistent volume, right, we need to understand the persistent volume is a unit of storage in a cluster, right? So it's an object within a Kubernetes. So when you just like you can create a pod, you can create a persistent volume within a Kubernetes cluster. Now, once you have that persistent volume within a Kubernetes cluster, right, you provide some specification. You say, what is the size? What is the type? Et cetera, et cetera. It is provided by an administrator or dynamically using storage class. So you have a couple of supported storage classes available within the persistent volume. When you create that persistent volume, you use one of that storage class, right? It acts in a cluster resource, right? And persistent volume are the volume plugins, but their life cycle is independent of the pod. So they don't really relate with the pod. So you can kill a pod, the persistent volume still is intact. The moment another pod is up and running, which is given an instruction to use the same persistent volume, it will be able to use it and get the same data. So the data is not lost for you. It's an API object, which basically specifies the storage implementation, right? So it says a couple of things. So if you look into the YAML definition of that persistent volume, you see that it uses a storage capacity 5 gigabyte, and the volume mode is file system. And what is the access mode? Like it has a read write once access mode. And then it has something which is important is that storage class name, right? Using this storage class name, you identify this persistent volume and attach it with your pod. Now, how that life cycle really looks like. So you create a pod, which basically uses a container within that, and then use something in between, right? That is a persistent volume claim. In this case, it is marked as PVC, which essentially interacts with the persistent volume through the storage class mechanism. So you have a persistent volume object created, defined with all the information, and storage class is one of the important thing. And you, when you create the pod, you don't create it directly pointing to that persistent volume. You point it via persistent volume claim. So you also need an object called persistent volume claim in the Kubernetes cluster available before you can use that, right? So that's a request mechanism. Now, in terms of storage class, this persistent volume is defined with different properties, and that includes performance, size, access parameter, whether read write or read only, and then it is allowed by storage class objects. So If you allow to expose a persistent storage, a persistent volume to user while abstracting the implementation specification, you will not be tightly coupled. You always will be loosely coupled. Now, there are various different storage classes available to pick up from. So, depending on the type of work you are doing, you can choose the storage class and then use it within your persistent volume. Now, a Kubernetes admin can actually create different type of storage classes and then give the user a variety of performance alternatives like SSD kind of storage class, which will be faster access. So if you're doing a lot of read write via file, you should choose that. If you are only, let's say, dumping the record but not reading it, maybe you can live with a slower storage. If it is only picked up on an occasional basis, maybe slower storage is fine. So it depends how your file is being accessed. One of the key component is the persistent volume claim. That's where the real game is, right? It uses a request for storage, right, from a pod perspective. It looks like a pod. So what happens when you create a pod, you use this persistent volume claim name to map a drive, right? You don't use the persistent volume directly. Now, it specifies a couple of things by which, just like selector in the deployment, through level name, it can fetch the pod through some of the criteria given in the persistent volume claim. You can actually pick up the persistent volume available in the cluster. So it uses things like storage class, sizes, etc. Depending on the availability, it will bind the persistent volume and then it'll be used by the pod. So to see the YAML definition, you will find that this is now a persistent volume claim or PVC, which can be an access mode or read write once. So this is one selection criteria. So it will try to find a persistent volume having the same access mode, read write once. Now in a cluster, you can have many persistent volumes available, right? So if it matches for any one of these persistent volumes available in the cluster, it will pick up from there. It'll also check the volume mode as a file system and then the required storage. Now, this is 8 gigabyte. So if you create a persistent volume as a 5 gigabyte, which you have seen in my earlier screenshot of the YAML, then that will not be picked up because that does not have enough space available. So you should pick up, or the system will pick up, a persistent volume which has got enough free memory which can accommodate this 8 gigabyte. Okay. So the moment it finds any persistent volume hanging around with more than 1 gigabyte of space, it'll go ahead and pick it up from there and it'll be blocked. So if you, let's say, have 16 gigabyte of persistent volume hanging around, and you create a persistent volume claim with 8 gigabyte like this one, yeah, it will allocate that 8 gigabyte. So now your persistent volume will only have 8 gigabyte available. So if you create another persistent volume claim asking for 9 gigabyte, then that persistent volume, which has only 8 gigabyte left, will not be able to serve it, right? So it will not be able to bind it. So the binding will not happen. And also another important criteria is the storage class time. So it has to match all these things to be able to pick up a persistent volume, which is already available in Kubernetes cluster, right? So that's how this binding happens. And this is quite dynamic in nature. So imagine that you bring up a new persistent volume, which has got more power, more capacity, matches the storage class name and the access mode and the volume mode, right? If it has all those criteria matched with a largest capacity, and then if the persistent volume is binding, it'll probably pick up the new one because it has got more power, right? So you basically end up getting a lot of options by default. But for your pod, you just need to care about the persistent volume claim. The binding happens for you, but the claim will then use that binding to reach out and save the actual file into a physical location, right? Persistent volume lifecycle. Persistent volume is a cluster level resource, and the persistent volume claim, or PVC, is a request for persistent volume resources. Now, the PV and PVC interaction lifecycle begins with provisioning. Then the binding happens. Then it starts getting used by the pods. And once the pods are cleaned up, the reclaiming can happen when new pods are trying to use the same PVC. Now, the persistent volume lifecycle in the terms of provisioning can happen in two different ways. One is the static way, another is dynamic way. The static way, cluster administrator creates the persistent volumes. The created persistent volumes are found in Kubernetes API. It contains information about cluster user storage resources. Dynamic provisioning, cluster dynamically provision a volume, happens when the static persistent volumes provided do not match with the persistent volume claim. Cluster uses the default storage class. Now, persistent volume lifecycle binding, which we discussed earlier, also is quite interesting stuff, right? So you see when you create a persistent volume in Kubernetes, and then you create a persistent volume claim, giving all those instructions, you will find the status of the persistent volume claim. Either it is trying to find that available persistent volume or already bound with an existing persistent volume. So that status will indicate and tell you what is the persistent volume claim looks like, right? And once it is being found, it will bind with the persistent volume, right? And then you will be able to interact with the matching volume through that persistent volume claim via your pod. So your pod will only think about that persistent volume claim, and then behind the scene, it can map with anything available today. Now, this is something heavily used in a stateful kind of nature in an app microservices world. If you have a stateful microservices and you don't want to really rely on the pod's life cycle, rather want to store the state, you can use this approach to do that, right? So it will basically allow you to have that data stored outside. Now, when you have that persistent volume claim, this will allow the user to schedule the pod. So if you, let's say that I am going to roll out new pod within a deployment, and they all use persistent volume claim. As long as the claim is bounded, the pod will be created, right? And then it will have all the things. Now, what happens when you are done with your work? Let's say your pod's activity is over, which uses a persistent volume claim to map a drive. Now, ideally, in an application space, you should remove the persistent volume claim object from a backend server perspective. So you say, not only delete my pod or deployment, but also delete this persistent volume claim. By deleting a persistent volume claim, then the persistent volume object, which is the actual storage, is freed up, right? And it can be reclaimed by another set of persistent volume claim behind the scenes. So this way, you will be able to leverage the same persistent volume for multiple different purposes, right? It can be retained, recycled, or deleted, the volumes, right? So the volumes you can retain it as long as you want. So in scenarios where you may be storing or retaining the log data for a longer period of time, you can also use this concept. If you are, let's say, only dealing with it on a short-lived thing, you can do that. Now, this is a Kubernetes cluster resource, right? So you don't see it within your namespace. the persistent volume, so it is at the cluster level. So when you say get request, you get to see that in a cluster level. Now there are a couple of persistent volume plugins available, right? Which basically enables various different other storage resources to be available within a Kubernetes cluster. So it is not always mandatory or a requirement to store file within the Kubernetes cluster, because we now start doubting about the reliability of my Kubernetes cluster as well. Instead, what I will do, I'll use Azure File, Azure Disk, or AWS Elastic Block Store, or GCP persistent, Google Cloud Persistent Disk, or vSphere Volume, all these cloud-based solution as my persistent volume, and map it with my persistent volume claim, right? You can also use dedicated file physical storage drivers, right? So you can use NFS, iSCSI, Fiber Channel, etc., which are not part of the operating system machine, but they are external specialized storage mechanism. You can also use this proprietary storage platforms available. So you have options available. These are all plugins, so you can attach as and when you need them. Now, in summary, what we have discussed about the overview of the Kubernetes networking, we understood the architecture of the networking, how the networking comes handy when you want to interact between pods outside of the cluster, inside of the cluster, and within the pod between the containers, how these things happens. Because you need to understand, even if you are, let's say, not exposing those services outside of the Kubernetes, it still needs to be observable, right? It has to be discoverable thing, because then otherwise the Kubernetes itself will not be able to monitor it from a health perspective, from a probing perspective. Now comes to the volume, where we discussed about the most important part, that is persistent volume, to be able to understand how we can retain the activity even when we kill the pod, right? And there are two different ways. One is ephemeral storage in the node, and another is persistent volume, which is outside of the node in the available within the cluster, or even using the plugin to bring in some cloud storage, which is not at all part of the cluster, and finally using the persistent volume claim to do a soft handshake and be able to use that volume. So with this, thank you very much, and see you in our next lesson.